empirically determined that 9 o'clock is far too early for IIT Madras students. But nevertheless, we'll start, and we go on the assumption that by the time Srikrishna gets to his table of contents, most of the people will have arrived. And so again, it's my pleasure. We have a new speaker today. We haven't heard yet, so that's Srikrishna Sahu. Many of you know him who are in mechanical engineering. But I've asked him to give a short self-introduction. But I can say one thing, that he did the doctorate the doctorate at Imperial College under the supervision of Yanis Hardalupis, a good friend of mine. I'm a little bit older, so I know all these people. and so I know a little bit the work that he was doing there. And that's a very good school, Imperial College. And I think he's brought some of that know-how here to Madras. And he's going to try and convey some of that know-how to you now. And I think it's in the direction of multi-phase flows, but all in multi-phase flows. But the floor is yours, Srikrishna.
Good morning. Myself, Srikrishna from Thermodynamics and Combustion Lab in the Department of Mechanical Engineering. First of all, I would like to thank Professor Tropia for coming up with this idea of this short-term course on measurement techniques in interfacial flows, and also for organizing this course. Also, I would like to thank Professor Arvind for coordinating and doing all necessary arrangements for the course. First of all, it's a privilege to talk about optical techniques when we have an expert like Professor Tropia in the audience. So now I will start. So the topic of my talk is on planar volume imaging techniques in two-phase flows. So this is the outline of the talk. So I will begin with a brief background, and then I'll spend some time on PIV for single phase flows, because not all of you may not be aware of details of the technique. So before I go to PIV for two phase flows or dispersed flows, and then I will talk about PIV lift based techniques for two phase flow, for simultaneous two phase flow measurements, and then measurement of particle number density, and then volumetric laser induced fluorescent or VLIF. So what are dispersed multi-phase flows? So they refer to flows where particles are suspended in turbulent fluid flows. So when I say particles, this means they can be solid, liquid or gaseous particles. For example, let's say air bubbles in liquid. So there we have gaseous particles in liquid flow. On the other hand, if you see a spray, there we have liquid particles in a gaseous flow. Or flow of slurry, where we have solid particles in liquid flow. So the fluid flow, the fluid flow basically refers to the carrier phase that carries the particles, which can be either liquid or gaseous flows. Now, the flow being turbulent is not a restriction. It can be laminar flows also. But in this talk, the flows that I will cover, they are turbulent. So due to stochastic nature of both the carrier phase turbulence and the dispersed phase distribution, the problem of understanding the turbulent dispersed multi-phase flows are much more complex compared to the single phase flows. Now, what are the roles of experiments in understanding the dispersed multi-phase flow? First, experiments are crucial for validation of models and simulation results. Second, it is also important to develop new numerical models. So this is only one example where the rate of change of turbulent kinetic energy of the carrier phase is presented, and this equation was developed by Chen and Dood. So you see that the left side represents rate of change of turbulent kinetic energy of the carrier phase when particles are present, while the first term shows the same without particles. And there are some additional terms which appear, and they contain correlation between the particle phase velocity fluctuations and the carrier phase velocity fluctuations, all these correlations. And in addition, you see there is correlation with the particle concentration also. Okay, so in order to model these terms, experiments can play an important role. Measurement of these terms can direct us to develop new models. Now, next thing is that we need, for detailed understanding, we need information not only about the dispersed phase, but also on the carrier phase. So mostly in dispersed multiphase flows, the focus is on dispersed phase only, on characterizing dispersed phase. For example, particle size, particle velocity, particle number, density. However, at the same time, characterizing the carrier phase is also important. And we need not only basic statistical quantities, for example, mean, standard deviation, but higher order statistics, for example, these correlations. And in order to measure quantities like this, we need to measure both the dispersed phase and the carrier phase at the same time. Okay, so and that is what causes, that is what basically causes significant challenges to experimentalism. Okay, so as I said, I will focus on the planar and volume imaging techniques, though there are many other techniques available. So here we are talking about basically whole field measurements, where we at any instant of time we measure some region of the flow. This is in contrast to the point measurement techniques. For example, say pitot tube or hot wire, where measurements are taken at a point. These are intrusive techniques. As far as non-intrusive techniques are concerned, we have also laser Doppler velocimetry or phase Doppler anemometer, PDPA, where measurements are taken at a point. Now, the whole field measurements have some advantage with respect to the point measurement techniques, that it avoids multiple measurements. However, this is not the only advantage. Importantly, it can give some statistics, for example, 2-point statistics, okay, which can only be measured when we have whole field measurements. And this also facilitates visualization of particle distribution and to understand other phenomena, for example, clustering of particles in flows. So, among these techniques, I will talk about mainly two techniques. First one is particle image velocimetry technique, which is well suited for the whole field measurement, and it has received wide acceptance. And then laser induced fluorescence based PIV techniques for simultaneous two-phase flow measurements. The lift-based techniques are also suited for characterizing the primary liquid breakup process. So I will briefly go over that. Okay, so first, what is particle image velocimetry technique? So as the name implies, in this case, we image particles in a flow. So why particles? So in this case, we add particles to a flow such that the particles can track the flow. These are known as tracer particles. So we add some particles, so we are not imaging the flow or the fluid, but the particles rather. So that is why it's called particle image velocimetry. And it's a two-step process overall. First, acquisition of the images, and second, processing of the images. So both are equally important in this technique. So as far as the principle is concerned, as you can see here, so we add particles and we illuminate that with a laser sheet. So the particles scatter light which are captured by a camera, and we capture two images in a very short duration, and we try to correlate group of particles in one image. Basically we track, you can say, group of particle in one image in the to the other image, and that gives the velocity of the group of particles, not even individual particles. Okay, so this is the basic principle of PID. So this may sound very simple, okay, but execution of the technique, it requires very much careful thought. Okay, so first, tracer particles. So as I said, the particles must be able to follow the fluid motion. So how do you ensure that the particles you are adding, they follow the fluid motion? Now, when we talk about turbulent flows, what is fluid motion? Are we talking about mean? Are we talking or the turbulent eddies? Now, you know that turbulent eddies themselves has a wide spectrum. You have large scale eddies that scale with the physical dimension of the flow, while you have, on the other hand, you have Kolmogorov scale eddy, which is the smallest eddy that is possible, which is much smaller than the large scale flow. So how do you know which eddies it can track? So basically we calculate Stokes number, which is basically the ratio of the particle relaxation time to some time scale of turbulence. So you calculate the Stokes number, and if the Stokes number is much below, let's say 0.1, this means that you can consider that as tracer particles. However, in order to calculate Stokes number, you need the information on the turbulent time scale. But your intention is to measure the time scale of turbulence or to characterize the turbulence. So how you would know beforehand the time scale of turbulence such that you can calculate Stokes number? I hope it is clear to you. Usually we consider the particles which have very small Stokes numbers, less than 0.1. But how do you estimate the Stokes number? Because you haven't done the experiment. So to begin with, some estimate of the time scale of the flow is required. Okay, and now it may happen that Stokes number is less than 0.1, but that Stokes number is based on large scale eddies. So when you consider smallest eddy, it is possible that the Stokes number is higher, such that the particles don't follow the Kolmogorov scale, let's say. So the velocity that you measure cannot give you the Kolmogorov scale. Okay, so it is not, so one has to be careful while selecting tracer particles. These are different particles that are typically used. So as far as particles in air flows are concerned, typically 1 to 10 micron or 5 micron particles are assumed to be tracer particles. However, that's an assumption. Whether those particles follow all turbulent eddies starting from Kolmogorov scale or not, that has to be checked. And it also depends on what is the purpose of the experiment. Okay, if you want only to characterize, let's say, basic turbulence quantities, like say mean, apart from mean, standard deviation, if that is the only purpose, then you may not resolve till Kolmogorov scale. But if you want to resolve the whole turbulence spectrum, you have to make sure that the particles follow the tracer particle, the Kolmogorov scale. Okay, now the other important component is the light source. So we know that means when we illuminate the particles with a light source, they scatter light, and that is what you capture. However, the scattering intensity depends on many parameters as shown here. Okay, out of that, particle size is quite an important parameter. So now this is contrasting. In one hand, we say that the particle size should be much smaller such that they can follow the fluid. On the other hand, we want to image them also. And typically, the scattering intensity is proportional to d square. So if the particle size is small, then the scattering intensity will be also be small. So this means that we need a high power light source, and that is the reason why we use pulsed lasers, typically ND-YAG or ND-YLF lasers. However, again, this is not a restriction. For example, if we are considering a flow of particle in a liquid, then the particle size is typically larger, where it is possible to use continuous wave laser. Okay, so these are some features of the solid state, the laser, but I will only talk about this one. So the duration of the laser pulse, that is very important. So typically that is of the order of few nanoseconds. So why is this so? This is because the laser pulse duration in this case would be mostly much smaller than the smallest time scale of turbulence itself. So what does it mean? This means that virtually you can freeze a flow. Actually, there is nothing called an instantaneous time in an experiment, because the laser pulse has certain duration. So it is not, theoretically it is not instantaneous, but we can assume the image to be instantaneous if the pulse duration is much smaller than the time scale of the flow. Okay, typically that is the case because this sort of time scale is not encountered in typical flows. I mean, the smallest scale is always larger than this laser duration. Okay, so one has to carefully design the laser sheet optics. So the technique is a planar technique, which means that we illuminate a plane. Now again, in practice, there is nothing called a plane. You always illuminate a volume, because a laser sheet has some thickness also. Okay, and we want this thickness to be as minimum as possible. Why? Why we want that way? Otherwise, the particles, we will image particles within a large volume. So we would be averaging in the depth direction. So we want, and also this way we can increase the laser intensity. So that is why we use a laser sheet optics. So this is a very simple configuration to create a laser sheet from a laser beam, because the laser as such does not give you a laser sheet. You have to create a laser sheet. So here you see that using a pair of cylindrical lens and spherical lens, a laser sheet is created. So this part is known as the beam waist, and your measurement region should be around this. Okay. Okay. So then imaging system. So typically CCD or CMOS cameras are used. So the most important aspect here is that the camera should be able to operate in double exposure mode. Double exposure mode means for PIV we need 2 laser pulses, as I mentioned, within a short duration of time. So during that time we should have the camera shutter which is open for distinctly for corresponding to these 2 pulses. So double exposure cameras are cameras with double exposure modes must be used. Okay, so this is about the synchronization of laser and camera. The laser and camera have to be synchronized. They have to be operated simultaneously, such that whenever we have a laser pulse, only at that time we should capture the image. Okay, so here I will show a video of particles.
Might have to take the laser. Go back to the normal. No.
So here I show a video where we see flow past a cylinder and some particles are added to the flow. So you can see the particle motion, but this is not an ideal PIV image. Why? This is because here you see the particles as streaks. You don't see individual particles, which is a must for PIV. You see streaks. So in this case, one can calculate the streak length, and if you divide that with the camera exposure time, that will give you some estimate of the particle velocity. Okay. However, as obvious here, it is difficult to identify individual particle streaks, and definitely you will get into measurement uncertainty. Okay. Okay, so there are some important steps before you start the experiments. So how do we decide how much seeding we need? Okay, so there are some rule of thumb. For example, within your interrogation window, you should have typically say 5 to 15 particles. So this is a typical PIV image where the flow is seeded with tracer particles. So we, as I said, here we track group of particles. So the image is divided into certain number of interrogation windows. Okay, this is the first image. Similarly, you have the second image, and we do cross correlation of the two windows, and that gives the particle velocity. And here the time delay between the laser pulses have to be also optimally selected. So how do you decide the time delay? If the time delay is too small, then you won't see movement of particles at all. Or the particle movement, if it is say few pixels, 1 or 2 pixels, then obviously you will encounter more uncertainty. If the laser delay time is too large, then you may lose the correlation. Okay, so this has to be optimally selected. Okay, I'm not going to detail into the image processing. So as I said, we have an interrogation window and a search window. So you do cross correlation, and depending on where the cross correlation peak lies with respect to the center of this window, we can find the displacement. So in this case, we can find the displacement in the x and y direction. You know the laser pulse delay time. So if we divide displacement by time, we get the velocity. So this is how the technique works. Okay, I won't go detail into this. Okay, another thing is how many image pairs we should capture. How do we know how many image pairs we need? So that depends basically on the aim of the experiment. What do you want to measure? If you, in all cases, all the statistics that you measure must be statistically convergent. So accordingly, the number of images that you need to measure only the mean velocity is less than what you need for standard deviation and for other quantities like vorticity, 2-point correlation, higher order moments. So basically, as you go towards higher order moments, you need more and more images. But for all cases, you must check the statistical convergence. So how to check? So first you consider certain number of images, let's say 500 image, then calculate a statistics, then 1000 image, 2000 image. So go on doing like this till you get convergence. So then you know that, okay, this many images I need. Okay, so in general, the PIV post-processing is a very important step. Basic knowledge on statistics and turbulence are essential. Okay, the classical PIV technique has been extended to stereo PIV, for example, where you can get two-dimensional but three-component of velocity. Tomographic PIV, where you do volumetric imaging, where three-dimensional, three-component velocity can be measured. Similarly, high-speed PIV, where you use a high-speed laser, but that also needs to be in double pulse mode. So you have two pulses, okay, and then micro PIV. Okay, so now we will come to the main part of the discussion. So how do we measure the dispersed phase by PIV? So, okay, I have this technique. Now instead of the tracer particles, I have a multi-phase flow. For example, let's say I have a spray. I don't have to seed anything. Already particles are there and I do PIV measurement. So what do we get? So I will show an example here. So here you see, these are the PIV images of the spray and these are the result. So here you get the velocity. Now this velocity corresponds to what? This velocity corresponds to the droplet. Okay, but if you see how much meaningful these measurements are. Why I am saying this? Because what do you measure is basically you are tracking the velocity of a group of droplets. So in the previous case you had tracer particles, but now you have group of droplets and each droplet have their own velocity. Okay, so when you measure droplet velocity here, this corresponds to which droplet or which droplet size. So you eventually you obtain a droplet velocity or some kind of size average droplet velocity that does not correspond to any droplet size. Okay, so one has to be careful while interpreting the results. Okay, of course it gives an order of magnitude of the droplet velocity. Okay, but it depends on what is the purpose. For example, if you want to study interaction between the droplets and the airflow, there information on droplet size, droplet velocity conditional on droplet size is required. But here you don't have any information of droplet size. Okay. Okay, so now we will go to the two-phase measurement techniques. So how do we measure the other phase, that is the carrier phase? So for that purpose, what I would do is that I would add seeding particles or tracer particles in the carrier phase. Okay. For example, let's say you have a spray where you have liquid particles in airflow. So I will add some tracer particles to the air and I can do a PIV experiment where I will see the droplets as well as the tracer particles. Okay. So now, how do we measure the carrier phase? If we simply process this, you get carrier phase velocity or droplet velocity? You don't know. Because if the droplet size is larger, obviously it will be biased towards the droplet velocity. But you get some average velocity again. So this means that the two phases must be separated. So we need phase separation technique. So you can say that, okay, fine, then I know that scattering intensity is proportional to d square. So the intensity of the tracer particles should be much smaller than the droplets. So I can put a threshold and eliminate all the particles such that I have only tracer particles and process that. So similarly, I can get the particle image separately. I can filter that and use PIV algorithm for the particles only. However, unfortunately, this approach does not work. This is because the particle size distribution often overlap. In this particular example, what I had shown, the particle size appears much larger than the tracer particle size, but in actual case that may not be possible. Okay, for example, say in a spray, you have particles ranging from 5 micron to 100 micron, and the average size is about 20 micron. So distinguishing a 20 micron droplet from a 10 micron tracer is not easy. So obviously this would lead to issues in separation, and this is known as cross-talk between the two phases. So now what is the alternate? One of the alternate is using lift-me technique. So in this approach, what we can do is that we can add some fluorescent dye to either particles or to the tracers as shown here. So what is laser-induced fluorescence? Laser-induced fluorescence refers to a technique where we add some fluorescent dye to a liquid and illuminate that with a suitable laser. Now then the liquid absorbs the laser light, the liquid molecules will go to the excited state, and when they fall back, they emit the fluorescence light, which has the wavelength different from the wavelength of the illumination source. For example, if you take water and put rhodamine dye and illuminate that with 532 or green light, then they fluoresces towards the red light spectrum. Okay, so the spectrum shifts towards the red light. So then I can put a suitable filter and filter out the green light and capture only the red light. So this is the basic principle of LIF. So we can use that approach. So you can add dyes to the particle if you are using liquid particles. Otherwise, you have to use the dye for the tracer particles only. Okay, so then, okay, I will go here later. So then we can image the two. For example, consider this case. Here we have the liquid particles which is tagged with some dye, and then we have the tracers. Okay, when we illuminate that with, let's say, 532, then in one camera you can capture the fluorescence images of the droplets only. Here you won't capture the tracer particles at all. Okay, this is because tracer particles are not tagged with any dye. While in the other camera you get both. This is the me-scattering image. This is the normal image. You get both the droplets and the tracer particles. Now because you have imaged the droplets separately, you can filter it out and get only the tracer image. So this is one way. The other way is to add fluorescent dye to the tracer particles such that you image only tracer particles without any droplets. And here you have droplets and the tracer particles. Somehow you have to filter out the tracer particles and you get the droplets. And then you process these individual images to get the respective velocity field. So here phase separation in the post-processing is involved. So when you post-process, then here or here you have to, in your post-processing, image processing, you have to do the phase separation. While it is also possible to separate the two phases during the image acquisition itself. Okay, so for example, so there are different approaches okay, where people use two different lasers. Okay, due to time restriction, I am not going detail into it. So here in this case, these people, they used two different fluorescent dyes for the liquid particles and to the tracer particles. So when they fluoresce, the peak of the fluorescence spectrum would be different for the liquid and for the tracer, and accordingly you separately image them. Okay. However, one limitation here in this case is that if there is significant slip between droplet and the gas flow, if let's say the droplets are moving much faster than the gas flow, then the same delay time cannot be used. Let's say the droplet velocity is 50 meter per second, gas velocity is 5 meter per second. So if you use a delay time to capture the droplets, so the droplets would move by that time, but the gas would, or the tracer particles wouldn't move. They will be stationary. So how would you measure the velocity? Okay. So to avoid this, other approaches are also there. I'll just give you a flavor of what other people have done. Now, another issue is that whether you do the phase separation in the image processing stage or in the image acquisition stage, what happens in the tracer particle image, you have empty spaces where the particles are actually there. Okay, so the tracer particle image is not an ideal one as in the case of single phase PI. So that is the main problem. So here you can see, for example, in this one, you may not see here, there are particles which are removed. Okay, and this is a mask that represents where the particles are removed. So basically you imagine you have a conventional PIV image, but some empty spaces within that. So if that is the case, that affects the image processing or the cross correlation. So the cross correlation will be lost because of this. So here you see that that peak is gone. So in order to overcome this, people have used some masking algorithm. I'm not going detail into it. But with that, if you use the masking algorithm, again the peak can appear. However, still it remains as a challenge. Okay, so this is about the velocity measurement. The lift-me technique can be combined also to get size of the particles. So we know that me scattering is proportional to d square and lift intensity is proportional to d cube. So the ratio of that can give this shorter mean diameter. So this principle is exploited in this technique, which is known as planar laser sheet imaging or planar laser droplet sizing technique. But this can only give shorter mean diameter. It won't give, or a shorter mean diameter is basically a characteristic size. It won't give you the size distribution. However, unfortunately, this relationship is not always straightforward. Okay, so people think that, okay, it's a straightforward technique, okay, capture both LIF and me images, and that gives you size, that's it. But why? Because the scattering intensity may not be proportional to d square for all scattering angle. Similarly, the intensity of light within a droplet may vary. So because of this reason, this relationship may not hold good. So people have done PDP experiment, for example, where you measure the size and you compare the size between this technique and the other technique, and large differences they have observed. Okay, so now measurement of droplet number density. So mostly in two-phase flows, the focus is on the measuring the size and velocity of the dispersed phase, and sometimes velocity of the continuous phase, as I mentioned. However, number density or concentration of particles in a flow plays also a very important role, because that basically tells you how much, for example, how much liquid is present locally in a spray, how much liquid you have. So for that you need to know how many number of droplets are present. Then you can argue that, okay, so what is big deal? You have the PIV image of the particles, not tracers, and you count the number of particles. That gives you the number density. Unfortunately, that is not true, because that gives you only number but not number density. So when you talk about number density, this means number of particles per unit volume. Now what is the volume? Which volume we are talking about? So you can say, okay, well, that is the laser sheet thickness times the area of the PIV image. Unfortunately, that is also not strictly true, because the effective depth of a particle depends on its size because of this reason. So we know that the laser sheet is always Gaussian in nature. So depending on where the particle is, the intensity would vary. So it is possible that a small particle which is near the edge is rejected. So in the image processing, the first step is to binarize the image. So for that you have to put an intensity threshold. Okay, so by that process you would reject always these small particles just because they are near the edge, while a large particle, wherever it is, will be imaged. So this means that the effective depth is proportional to the size of a particle. Okay, so that can lead to measure source of error. Okay, and then we can use the PIV images to characterize clusters. I won't go detail into it. So using various statistical methods, we can characterize particle clusters. But here, one thing I would like to note here. So this is an image of spray droplets in a typical injector. Now, what you see here is that the droplet distribution is not homogeneous. Somewhere you have more droplet, somewhere there is a void. Now, if you use PIV for this to find the velocity, it may be possible that in your interrogation area in some regions you have limited number of droplets. So you don't have control over the seeding density as in the case of single phase flow. So that is an important difference. Anyway, so we can use the PIV images to characterize clusters using various statistical methods, for example, Voronoi analysis as shown here. And finally, till now I have been talking about planar technique, but volumetric techniques also exist. So the Tomo PIV itself is a volumetric technique where you can illuminate a volume of the flow, and there we can find the droplet position and 3-component droplet velocity. Though I am not aware of anyone applying Tomo PIV over droplets, I think so. It does not exist. But volumetric laser-induced fluorescence has some advantage. So in this case, basically, instead of creating a planar sheet, you create a volume and illuminate the flow. The advantage here is that the advantage compared to direct photography or direct visualization or backlight visualization is that the image contrast is quite good. So for example, in this case, a liquid sheet has been illuminated with a laser volume. So these are DSLR photograph, but these are VLIF, okay, where you can see some details, for example, perforation. So it is difficult to get this kind of images if you directly image it, let's say using backlight or front light illumination technique. And we have applied this technique in an atomizer called Slinger atomizer. It's a rotary atomizer where there are multiple holes and liquid comes out. So you see, so we have done this for different orifice sizes. So you see, especially when we go towards higher rotational speed of the atomizer, the direct photograph I haven't shown here, you won't be able to see anything. However, the VLIF technique provides good information. And finally, I will just quickly conclude. So this is also another volumetric laser induced technique only, where this is called optical connectivity, where the liquid is illuminated from the top. Okay, instead of illuminating the whole liquid from side, because in that case you will see the droplets also. So here the liquid jet is illuminated from the top. So the light is guided only till the breakup point. So here you see the difference between a normal shadowgraph image and the optical connectivity image. The breakup location can be objectively identified in this case. Okay, so that is the advantage. We have used this for a cross stream atomization of a liquid jet within an atomizer, and we could image both the liquid jet from both front and side view. So in this case, okay, so this is the typical front view, side view, and this is the front view. So what we have found is that the breakup mode, what we think is always like this, if you see the side view, but the front view also tells us that the liquid jet basically is transforming into a sheet before it breaks up. And if we take normal shadowgraph images here, means we don't see much. This is because there is this tube that always appears in the background. Okay, so I just gave some quick examples. So these are the conclusions. So PIV is a powerful optical technique for planar characterization of two-phase flows. PIV LIF based techniques have the ability to measure the both phases but simultaneously. However, one of the drawback is that we don't have information about the particle size. So if you have a strong particle size or large broad particle size distribution, then we will have to have the knowledge on the particle size as well as the particle velocity. Critical parameters during both image acquisition and processing stage must be carefully considered. And image processing also plays a very important role in the two-phase PIV technique. And the extension of these techniques, what I discussed to complex flow configurations, are still under investigation. So, thank you.
Thanks a lot, Srikrishna. I think this point is really important. There's still a lot to discover and to invent, you know.
These configurations.
You've invented a few things and I've invented a few things, and I'm sure you will invent a few things in your life. Okay, we always have time for questions, and you've thankfully.
Sorry, I'm 5 minutes
No, you've
late.
kept your time wonderfully. So let's start with some questions. I know some of you are already using these techniques, and some are for you that's new. But nevertheless, here's your chance to ask an expert.
Yes.
Let's start in the back here, and then we'll go over this side.
Okay.
So I have one question. So you discussed about statistical convergence when we are studying going to higher orders of details in that flow. So how do we study that convergence? Means if we are taking some image at some particular time, then we are we are reducing that time of imaging. Means we are increasing the FPS. Like we are taking more images in that time. So how do we understand that statistical convergence is reached?
No, the time does not matter. So you see, let's say at once you capture say 5,000 images. Then you calculate whatever statistics you want from those 5,000 images. Then calculate it for say 3,000, 2,000, 1,000, like that. And then you see how the statistical quantity varies with the number of images. Once you see that, okay, after 3,000, let's say it is not varying much, then you don't have to capture 5,000 images. You get only 3,000 images.
That's the engineer speaking. That's very practical. It's not a matter of number of images. It's a number of. It's not a number. A question of how many images. It's a question of how many statistically independent images you've got. You know, I mean, if you've got some trace here and you measure 5 million points between here and here, that doesn't get you closer to the mean. You have to have statistically independent samples, and then you say, okay.
Yeah.
But the practical way of doing it is exactly what he said. But in some cases where it's more difficult to actually compute your statistical variance of your estimator, you use what's called the bootstrap method. And if you go Google that and take a look at this, that's a very powerful method for determining variance of estimators, is the bootstrap method. But it's very close to exactly what you said. He's got it. I said the engineer because it's the practical way of doing things, not the mathematical way.
Yeah, but as Professor Tropia said, means it is very important that you know that you have statistically uncorrelated image. For example, let's say you have a sine wave. Okay, so if you consider, let's say the first part, 0 to 90 degree, and let's say you capture some 10,000 data points there, that won't give you the correct statistics. Because you are considering only part of a cycle. So you have to consider many cycles to get the converged statistics.
So we had here
Yes.
and then down here.
Yeah, you talk about synchronization between laser and camera. So it is some device are used for this, or like manually?
There are many standard. No.
Possible to do manually?
Manually means so sometimes the lasers give laser output can be connected to the cameras, but usually you won't be able to control. So it is not like we just want to synchronize once. We need to be able to adjust the delta t, okay, and the frame rate. All these parameters you should be able to, and it can be easily done. Means even using Adreno boards, people have done it. Very low cost.
So here, and then I think, did you have a question? Okay, so 1, 2, 3. So let's go.
Professor, so actually one part of the question you have already answered. One is that sign part that I was about to ask. The other thing is that I basically come from ocean engineering department. So we generally study with unsteady flows. So in that, when I study regular wave or any state of waves interacting with a structure, generally it becomes, it won't be an steady part. So there will be always a time dependent factor in that. So in that time, understanding the stochastic is very difficult. So how do we encounter the convergence rate in those?
I assume this is state unsteady, but there is some periodicity.
No, a periodicity will be there when.
So in that case, you use phase locked images. So this is called, so at a particular phase, you capture the image and you go on doing that for many cases. Okay, so you have an ensemble of images at a particular time. So this is called phase locked, and then you do this for other different times. So then you can see the time evolution of the statistics.
So you have a periodic.
Okay.
And even if the period's not exactly always the same, then you just, it's like with the heartbeat, it's not always exactly the same when we do medical. And then you have to adjust you have to compute the phase in each cycle, you know, where you were, to understand if it's not exactly periodic. Okay, go ahead. I think, no, in the back somewhere, yeah, thanks.
Yeah.
So you mentioned that calculating number density is actually very, like, you won't get the exact value from the scattering images. So is it acceptable whatever we calculate from the scattering images?
No, it's not about if it is acceptable or not. See, it always underestimates. Okay, about 50% underestimation is possible. It depends on what do you want to study. So if, let's say, you want to compare number density here and here, and or let's say in a radial direction in a spray, let's say, and then you can normalize with respect to one, say the center value, and see the evolution. That is fine. You are okay with respect to one, say location. You are normalizing. Okay, so you get the relative values. But the absolute values is the problem.
And then another question is the interrogation windows. Like when we do PIV for a spray or any droplet phase, case. So we would have, I mean, as you mentioned, either very few droplets or just no droplets in some areas of interfacial window. So what do we do in such a cases?
See, as far as PIV in spray is concerned, this will be always a problem. So what will happen in those cases? The correlation coefficient will be low, and that part will be rejected. You can reject that. So, but this means that you have to collect large number of samples to get some statistics.
Like I mean, number of images you have to have.
Number of. Yes.
Is that a follow-up question then?
No, it's a separate question.
Oh, okay, yeah, go ahead, and then I think we have one in the
So
back.
let's say if I have a vortex inside a fluid and I'm doing a PIV for the to calculate the velocity of that vortex. But for that I need a Stokes number so that I can know that the particles are still following the path lines of the vortex. But in an experiment, it may happen that particle, instead of following one path line, due to its motion, will go to another path line. Will start to follow another path line. Then the calculation of both the velocities are different, correct? Because the vortex has some other velocity in one path line and other has the another velocity.
First of all, the turbulent flows, in turbulent flows, you have turbulent eddies, which are always vertical in nature. So it's not like in some cases you don't have and in some cases you have. It is always
It's
like
always there.
But here we are calculating the velocity with a very short duration of time. We are not calculating the path line of the tracer particles. So at any instant of time you can calculate the velocity.
So we are not concerned with the gross flow of the particles.
No, so that is what. So the duration, the time delay between the two pulses should be much smaller than the time scale of the flow. So at that time instant, this is the velocity. You can calculate. I hope that answers your question. We don't calculate the path line of the tracer particles.
Go ahead.
Yes, sir. In PIV alignment technique, like we have two cameras and we are taking one single image, right? And we're doing some subtraction of image. So how we are ensuring that both cameras are taking the same image, like same area?
How do both cameras see the same view?
Yeah, exactly.
So you have to do a calibration, a proper calibration. So you need to set a target plate at the measurement location and visualize. First do that. So visualize from both cameras, and you need to quantify the error. So let's say you have some marks. Okay, some circle marks. Then you image through both cameras and try to adjust, and then you should have the calibration coefficients to project them on. So if you do a proper calibration, then you can project them on the object plane. So, and both would reach at the same point.
So like there should be some accuracy because like manually we can reach micron level accuracy.
No, then the calibration takes care. Because when you project it to the object plane from this camera and from this camera, but let's say there is a point which is at say location x location 2, y location 2. So in the image, in both images, the locations may be different, but you are projecting them to the same point.
Maybe subpixel also, sometimes it's subpixel.
I didn't talk about that. So
Yeah.
subpixel accuracy.
You have to
Yeah.
guess a little bit, but we've got
What is the laser thickness? I mean, laser thickness, minimum thickness supposed to be maintained. It depends with the particle size, or
No, it depends on the flow. Yeah, particle size is usually much smaller than the laser sheet
Laser
thickness. Laser sheet thickness is like say 1 millimeter, 500 micron, something like that. Laser sheet thickness you can get. So it depends on the flow. So if there is no much three-dimensionality, then maybe somewhat larger is fine. But if let's say there is a strong swirling flow, so there the laser sheet thickness has to be carefully maintained. Otherwise the particles would leave. So if you make it too small, they will leave the
yes.
volume. If you make it too large, then you basically introduce averaging.
Is there any standard to follow?
No, so you have to do it and
But it's commercial equipment. It's usually, you don't have to build it yourself. You can buy these things. It's laser sheet arms, that use the sheets and allow you to adjust the
They're
thickness a little bit. And
They're
the
very
more you pay,
expensive.
the more you
No,
get.
No, I'm helping my friend. So
Yeah.
when I am doing that part, I may be like struggling to maintain that thickness
Yeah.
relationship thickness. So, okay, sir. Thank you.
It's not trivial.
Mm.
Not trivial, but it's how we do your time. Some further questions before we break?
Yeah, integration, interrogation window you talk about. So there we do correlation. Suppose it is possible that we are getting good correlation, but it is giving wrong velocity field. Like you understand means like
Sometime it is possible. So you are talking about some outliers, I think. So
because suppose if I am taking the top left corner, so from there it is correlating some middle region. So that time it may give. So suppose at the middle it is giving good correlation. So the correlation is highest there. So that time it may give wrong velocity field. Because
sometime it
because
is
the
possible that you have good correlation, but you can clearly see that it's an outlier. So the local velocity would be say much larger than the surrounding. So there are different methods to remove the outliers or replace it with a replace it by suitably interpolating the neighborhood velocity.
so that the correlation window has to be just nearby to the search like
No, first
the
of all, you
initial.
should not, the correlation window, you should not go towards the edge. So the edge you should leave out.